In the previous video, we examined the prior indifference fallacy. That happens when in the Bayes theorem, which by now you know can be written like this, we implicitly and wrongly assume that the base rate BR equals 1/2. In that case, you can see these disappear, and we're left with this, which says that the posterior probability PP equals the true positive rate TPR over the sum of the true positive rate and the false positive rate FPR. Since the denominator is usually not very far from 1, PP is quite close to TPR, and with symmetric evidence is exactly equal to TPR. Remember, PP is the probability of the hypothesis in the light of the evidence, and TPR is the probability of the evidence if the hypothesis is true. Hence, we say that prior indifference results in the inverse fallacy. Among the various examples discussed in the blog, we saw that of the child footballer, where a test or equivalently an expert coach, endowed with a high degree of proven accuracy, predicts that the child will become a football champion. Under prior indifference, the probability that the child will become a champion in the light of this prediction is very high. But that turns out to be a huge mistake, because once we take into account the fact that football stars are rare, that is, the base rate of football stars is very low, then the true posterior probability, though much higher than the prior, remains very low in comparison. In our example, we had 2% versus 95%. That is a huge gap between actual and perceived probabilities. We concluded the video saying that such a gap, if it existed, would obviously be the basis for an extremely advantageous bet. So this is prior indifference. Why is it a fallacy? It is because, in most cases, it is not true that the base rate is 50%. Clearly, in the child footballer story, it would be crazy to assume that the child had a 50-50 prior probability to be a champion. That is not what the father is thinking. Before the coach's prediction, it is very clear to him that there is only a very small chance of that happening. But after the prediction, the low base rate, so clear and consequential until then, is driven to the background. The father loses track of the appropriate reference class on which to calculate the base rate, his child becomes uniquely incomparable, and the base rate fades away. The father assumes perfect ignorance. He is blinded by evidence. So while Bayes' theorem is always true, it is like 2 + 2 is 4, or like Pythagoras' theorem, the inverse fallacy, or prior indifference fallacy, should be seen as a tendency, not as a systematic flaw. Bayesian updating normally works very well. People are smart and do not automatically commit the inverse fallacy. It is like with optical illusions. We can and normally do understand that we are making a mistake, but the illusion does not vanish once we understand it, and in many circumstances it can have real consequences. So let's go back to our bet and take a closer look at it. The posterior probability PP measures the level of support that the evidence gives to the hypothesis. TPR and FPR measure the level of accuracy of the evidence as a prediction of the hypothesis. As we saw in the first video, a natural measure of accuracy is the average of the two true rates, TPR and TNR. TNR is the true negative rate, which by definition equals 0.5 plus half of the difference between TPR and FPR. According to this measure, perfect accuracy has TPR equal 1 and FPR equals 0, and therefore A equal 1. Perfect inaccuracy has TPR equal FPR, and therefore A equals 1/2. And perfect contrary accuracy has TPR equals 0 and FPR equals 1, hence A equals 0. An alternative measure of accuracy, A star, is equal to 2A minus 1, and is therefore the difference between TPR and FPR. A star has the advantage of being equal to 1 with perfect accuracy, 0 with perfect inaccuracy, and -1 with perfect contrary accuracy. But I prefer the first measure as it directly shows the insidiousness of perfectly inaccurate evidence. If I have no clue whatsoever about whether a hypothesis is true or false, I might as well toss a coin. Remember that if TPR equal FPR, evidence is unconfirmative and leaves the posterior probability equal to the prior probability. A perfectly inaccurate expert is not one that is always wrong. That would be a perfectly useful contrarian indicator. We all know a few experts that seem to fit the bill. A perfectly inaccurate expert is one that is right with a frequency equal to the base rate of the hypothesis, the proverbial stop clock that is right twice a day. In our child football story, we had TPR equals 100% and TNR equal 95%. Therefore, FPR equal 5%. The coach was very accurate, with A equal 97.5% and A star equal 95%. His prediction improved the probability of a champion from 0.1 to 2%, a 20-fold increase. But imagine instead that the coach called every child a champion. In that case, his TPR would still be 100%, he would still never miss a champion, but his FPR would also be 100%. He would always wrongly call champions all ordinary children. That would obviously be a perfectly inaccurate coach with A equals 0.5 and A star equals 0. According to Bayes' theorem, his prediction would be perfectly useless, leaving the posterior probability equal to the 0.1 base rate. But look what happens under prior indifference. With TPR and FPR equal to 1, the posterior probability equals 50%. A perfectly worthless coin toss forecast moves the perceived probability all the way to 50%. A perfect example of a perfectly useless predictor is Mr. Market. As many of you watching this video know, Mr. Market is a fictional character imagined by Benjamin Graham. If you don't know, you can find it in Chapter 8 of The Intelligent Investor. Mr. Market is, very obligingly indeed, always prepared to buy and sell any business at the current market price. For him, the price is always right. Hence his calls are totally uninformative, and the posterior probability of the hypothesis the market price is right, in the light of Mr. Market's pronouncement, should not differ from the base rate. What happens, however, if Mr. Market is perceived as an expert? In that case, under prior indifference, the posterior probability in the light of Mr. Market's verdict is also 50%. An investor who mistakes Mr. Market for an expert has fallen prey to the prior indifference fallacy. He is saying, I don't know whether the price is right or wrong, but Mr. Market, who is an expert, says it is right, so I believe him. By centering value at the market price, the investor is neglecting the possibility that the price might be much higher. Imagine, for example, that we value a company stock at 100. Assume that value is normally distributed around 100 with standard deviation 20. As we know, this means that there is an approximately 95% probability that V is between 60 and 140, two standard deviations. Imagine that Mr. Market prices the stock at 50, with P also normally distributed around 50 and, for simplicity, the same standard deviation of 20. For our purposes, we say that the price is right if it is equal or greater than V. The stock is fairly priced or expensive, i.e., it is not attractive. In this sense, the probability that a price of 50 is right is, according to our valuation, very low. It is this bit here, 0.6, the area to the left of the normal distribution at 100. While according to Mr. Market's valuation, it is 50%, the area to the left of his distribution. So here we are, 0.6 versus 50%. Again, a very large gap between actual and perceived probabilities, which makes it potentially very advantageous for us to bet against Mr. Market. Obviously, the gap depends on the market price. The probability that the price is right is 0.6 at a price of 50, but, for example, it goes up to 11% at a price of 75, again, the area here to the left of our distribution, and all the way to 50% at a price of 100. For Mr. Market, on the other hand, the probability that the price is right is always 50% at any price, because any price is right. Therefore, the size of the probability gap decreases with the market price. It is almost the entire 50% at a price of 50, that is 50 minus 0.6%, but it goes down to 50% minus 11% here at a price of 75, 39%, and all the way down to 0, of course, at a price of 100. So a 50% discount is considerably more valuable than a 25% discount. The gap corresponds to Ben Graham's margin of safety and reflects Graham's emphasis on the need for the margin of safety to be sufficiently ample. The gap also depends on valuation uncertainty. With the higher uncertainty, 30 for example, standard deviation of 30, the gap at 75 would go down from 39 to 30%. As investors, however, we are not so much interested in the probability that the price is right, but in the probability of a large return. So let's go back here. The definition of a large return is of course quite arbitrary, but as with the famous definition of obscenity, you know it when you see it. So let's call an obscene return a return of more than 50%. At a market price of 50, the probability of an obscene return, if value is 100, is 89%, which is the area here to the right of the value distribution at 75, which is of course 100 minus 11%. While according to Mr. Market, who thinks that the price is right and therefore value is 50, the probability of an obscene return is only 11%, which is the area here to the right of this distribution. So for us, the stock has about a 90% probability of an obscene return. So let's call it a pearl. And for Mr. Market, the same stock has only about a 10% probability of an obscene return. Let's call it a pebble. So we have transformed the 0.6 versus 50% probability gap on the hypothesis that the price is right into a 90% versus 10% probability of the hypothesis that the stock will have an obscene return. According to Mr. Market, every stock is a pebble. There is no such a thing as a pearl. Now, as it happens, 10% is a not unreasonable estimate of the base rate of obscene returns. For example, if you take the last 10 years, the percentage of US stocks with a market cap above 100 million that have had an annual return of more than 50% has averaged 14%. Even in 2008, believe it or not, about 1% of stocks went up more than 50%, followed by 33% of stocks in 2009. A calendar year window is of course arbitrary. For example, a stock may go up 50% and then down within a year. But it gives a rough idea and shows that 10% can be a reasonable, if maybe conservative estimate of the frequency of obscene returns. So Mr. Market's 10% probability is close to the base rate. When he calls every stock a pebble, he's not saying that the stock will definitely not have an obscene return. He is saying that the chance of this happening is 10%, in line with the base rate. So Mr. Market is right on average, but he really has no idea on whether any particular stock will or will not earn an obscene return. Imagine you're given 100 statements, half of which are true and half false, and you're asked to give the probability that they are true or false. So if you're sure that a statement is true, you should say 100%. If you're sure that it is false, you should say 0%, and so forth in between. Imagine that for each statement your answer is 50%. So you're 50% sure that the Pope is Italian, 50% sure that London is below the 50th parallel north, and so on. In a sense, you're well calibrated. You're right on average, since 50 statements are true and 50 are false. But at the same time, you're obviously perfectly ignorant. Likewise, if only 10 of the 100 statements were true, and your answer was always the probability that each statement is true is 10%, again, you will be right on average, but perfectly ignorant at the same time. Well, this is what Mr. Market says when he's asked what is the probability that a particular stock will have an obscene return. His answer is always 10%, right on average, but otherwise perfectly ignorant, and therefore totally inaccurate and uninformative, just like a coin thrower always calling head or a weather forecaster always calling rain. An investor who mistakes Mr. Market for an expert has fallen prey to the prior indifference fallacy. He is saying, I don't know whether a stock is a pearl or a pebble, but Mr. Market is an expert and he says it is a pebble, so I believe him. Again, by centering value at the market price, the investor is underestimating the probability that the price might be a lot higher. So let's go back to our valuation. We think the stock is worth 100, and with the market price of 50, the probability of an obscene return is 90%. The stock is a pearl. As such, we are very keen to bet against Mr. Market, who thinks the stock is a pebble. And the probability of an obscene return is just 10%. What more do we want, right? Let's go for it. Well, not so fast. We should be well aware that our valuation may be completely wrong. Mr. Market may be right. The stock is a pebble and is worth 50. Or worse, the stock may be worth less than 50. Even a lot less. If the company goes bust, the stock is worth 0. So a key question is, what can we do to make sure that we are not making a possibly big mistake? The intuitive answer is, we should look for conclusive evidence to push our 90% probability towards 100%, and thus prove, beyond reasonable doubt, that we are not mistaken, and the stock will definitely earn an obscene return. But that is not the right answer. To see why, let's take a detour. Dial M for Murder is a 1954 Hitchcock thriller. In it, Tony Wendes, who is married to Margot, conceives a plan to murder her after finding out she's having an affair with Mark Holliday, whose love letter he found in Margot's handbag. Tony had stolen the handbag and anonymously blackmailed Margot about the letter. Tony asks an old acquaintance, Swan, to commit the murder. The plan is that while Tony takes Mark out to a party, Swan comes into the flat where Margot is asleep, using Margot's latchkey, which Tony will have left under a carpet in the stairways outside the front door. Swan will hide behind the curtains until Tony makes a phone call. As Margot wakes up and answers the phone, Swan will kill her, open the garden door to simulate a burglary, and exit through the front door, leaving the latchkey where he found it. On the night, however, before entering the flat, Swan puts the key right back under the stairway's carpet. Then, as Margot answers the phone, he tries to strangle her, but she manages to stab him with a pair of scissors and kills him. Tony rushes back home and calls the police. With Margot back to bed, he takes a latchkey from Swan's pocket, which he thinks is the key he gave him to enter the flat, puts it in Margot's handbag, and places Mark's love letter in Swan's coat. The next day, Chief Inspector Hubbard questions the Wendeses. As there are no mud stains on the floor, he figures out that Swan must have entered through the front door, not the garden, and wonders how he got in. Tony claims that he saw Swan at the time that Margot's handbag got stolen, and suggests that Swan must have made a copy of the key. But Hubbard dismisses the idea since no key was found on Swan. The inspector concludes that Margot must have killed Swan because he was blackmailing her about the love letter. He arrests her, she is tried, found guilty, and sentenced to death. On the day before the execution, Hubbard visits Tony. He has grown suspicious of him after finding out that he's been spending a lot of money lately. In the meantime, he had figured out that the latchkey in Margot's handbag belonged to Swan. He manages to secretly swap raincoats with Tony, and after Tony leaves, Hubbard re-enters the flat using the key from Tony's raincoat. He has asked the police to release Margot and waits for her to enter the flat. She tries to get in using the key in her handbag, which she thinks is her key. But the key doesn't work, since it is Swan's key. So she goes around and enters through the garden door. This shows that she doesn't know anything about the key under the stairway carpet. Hubbard asked a police officer to quickly return Margot's handbag to the police station. Tony had gone there after finding no key in what he thought was his raincoat. So he gets Margot's bag, where he had put the key from Swan's pocket, and, as Margot had just done earlier, tries to open the door. But he also finds out that the key doesn't work, and is about to go around the back door when he realizes what Swan must have done with the key. He picks the key from under the stairway carpet and opens the door. He's just proved himself guilty. So, what am I talking about? Well, think of Inspector Hubbard as an investor. Think of Margot as a pearl and of Tony as a pebble. As he returns to the flat, Inspector Hubbard has grown suspicious of Tony. He thinks it is quite likely that Tony is guilty and Margot is innocent. Let's say he is 90% sure that Margot is innocent and 90% sure that Tony is guilty, i.e. 10% sure that he is innocent. These are the same probabilities that our stock will have an obscene return if it's a pearl and if it's a pebble. The inspector is looking for conclusive evidence to prove his case beyond reasonable doubt. He wants to make sure he's not making a big mistake of convicting an innocent person. The investor wants to do the same about his stock. He wants to make sure he's not making the possibly big mistake of buying a pebble, or worse. As our 4 cases of conclusive evidence are named after the hypothesis of guilt, let's reverse the hypothesis and say that Margot has a 10% probability of guilt, here, and Tony has a 90% probability of guilt, here. Likewise, a pearl has a 10% probability of a non-obscene return. For our purposes, let's call it a market return. And a pebble has a 90% probability of a market return. So Margot equals pearl and Tony equals pebble. Earlier we asked, what can the investor do to make sure he's not making a big mistake? Well, let's see what the inspector did. He was 90% sure that Margot was innocent. What did he do? Did he try to push that 90% towards 100% and prove that Margot was innocent beyond reasonable doubt? No. He tried to prove her guilty. Let's look at the scene.
What is all this?
They talk about flat-footed policemen. May the saints protect us from the gifted amateur. Better prepare yourself for a surprise, Mr. Halliday.
Margot.
Hello, Mark. Where's Tony?
He's gone out.
When will he be back?
We're not sure. Was that you who rang just now?
Yes. Why didn't you let me in?
You've got a key. Why didn't you use it?
I did, but it didn't fit the lock.
No, and you know why, don't you?
No, I don't. Has the lock been changed?
May I have your bag a moment? Whose key is this?
I thought it was mine. I don't know.
What's going on here?
Your husband's explained this, you know. You can tell us all about it now.
What is it? I don't understand.
No, I don't believe you do.
Exactly. If Margot had opened the door, she would have proven herself guilty. The only way to open the door was by using the key under the carpet. And there was no way that Margot could have known about the key except that she put it there. Margot opening the door would have been what we called a smoking gun, positive conclusive evidence that proves the hypothesis of guilt. But she didn't. It is because she failed to open the door that the inspector became convinced of her innocence beyond reasonable doubt. His 90% probability of innocence moved very close to 100%, that is, the probability of guilt moved from 10% to nearly zero. But then something very interesting happens. The inspector tries to prove Tony guilty using exactly the same door test. Let's look at the scene.
Well, Mr. Halliday, have you got it?
I don't think so. Where's Mrs. Wendis' key?
It took me just half an hour to find it.
But if it was there, why didn't Wendis use it just now?
Well, he didn't use it because he doesn't realize it's there. He still thinks it's in his wife's handbag. You see, you were very nearly right. He told Swan that he would leave your latchkey under the stair carpet, Mrs. Wendis, and told him to return it to the same place when he left. But as Swan was killed, we naturally assumed that your key would still be in one of Swan's pockets. That was his little mistake, because Swan had done exactly as you suggested, Mr. Halliday. He unlocked the door, then returned the key before he came in.
And it's been out there ever since. And the key Wendis took out of Swan's pocket and returned to her handbag was...
Swan's own latchkey. Mind you, even I didn't guess that at once. Extraordinary. You know, it had always puzzled me that no key was found on Swan's body. After all, most men carry a latchkey about with them. And then I had a brainwave. I took the key that was in your handbag to his girlfriend's, Mrs. Van Dorn's, and unlocked the door of her flat. And then I borrowed her telephone and called Scotland Yard.
Why did you bring me here?
Because you were the only other person who could possibly have left that key outside. I had to find out if you knew it was there.
Suppose I had known.
You didn't.
Mark,
Yes, darling.
I think I'm going to have that key.
Inspector Hubbard?
O'Brien?
Yes. He's just left the station.
Right. Try and hang on just a little longer. Williams, he's just left the station. Give me a thump if he comes this way.
What happens now?
Sooner or later, he'll come back here. As I've pinched his latchkey, he'll try the one in the handbag. When that doesn't fit, he'll realize his mistake, put two and two together, and look under the stair carpet.
But if he doesn't do that, all this is pure guesswork. We can't prove a thing.
That's perfectly true. But once he opens that door, we shall know everything.
What'll you do then?
I'm to phone the Home Secretary personally. He's standing by for a call now.
And Mrs. Wendis?
We'll have nothing else to fear.
All right, Mark.
Yes, I'm all right.
Quiet now, you two.
What's he doing?
He's wondering why that key doesn't fit. He's going round to the back entrance. He's stopped again. He's looking at the handbag now. He's trying to remember when he put the key back in there. No, he's given up. I'm afraid we've had it this time. He's going way down the street. Hold it. He stopped again. He's turning round. He's staring at the key. Of course, that's Swan's key, isn't it? Now he's got it. He's coming back fast. He's remembered.
Hitchcock at his best. So, first of all, Margot asks the inspector, "Why did you bring me here?" The inspector explains the door test. He says, "Because you were the only other person who could have left the key outside, I had to find out if you knew it was there." Then Margot, about to faint, says, "Suppose I had known." And the inspector, "You didn't." There you are. It is the failure to prove her guilty that makes Inspector Hubbard virtually certain that Margot is innocent. Second, the inspector explains to Mark the test he's about to perform on Tony. It is exactly the same test. If he opens the door, he will prove himself guilty. "But if he doesn't do that," says Mark, "all of this is pure guesswork. We can't prove a thing." And the inspector, "That's perfectly true. But once he opens that door, we shall know everything." So you see, the inspector expects Tony to open the door because he's quite convinced he's guilty and because Margot, the other suspect, has just failed the test. But here is the interesting point. What if Tony had failed to open the door? That was entirely possible. Indeed, Tony was about to do so. Perhaps he had forgotten about it, or he wasn't focused, or perhaps he considered it more prudent not to use the key anyway. For whatever reason, Tony could have failed to open the door, just like Margot had done a few minutes earlier. Then, as Mark says, Tony's guilt would have remained pure guesswork. We can't prove a thing. But the point is that the inspector would have remained convinced of Tony's guilt, unlike with Margot, whose test failure convinced him of her innocence. Why such a difference? It is because conclusive evidence is not the same as perfect evidence. Let's see. Here on the left is Bayes' theorem with perfect evidence. Remember, perfect evidence is TPR equals 1 and FPR equals 0. It is cause and effect. Cause implies effect, no cause implies no effect. PP is the probability of the hypothesis if the evidence is positive. It is 100% throughout, independent of the Bayes rate. NP is the probability of the hypothesis if the evidence is negative. It is 0% throughout, independent of the Bayes rate. But conclusive evidence, here on the right, such as a smoking gun, is not perfect. While positive evidence is conclusive proof that the hypothesis is true, opening the door is conclusive proof of guilt, independent of the Bayes rate, negative evidence still depends on the Bayes rate. If the Bayes rate of guilt is small, as is the case with Margot, then a smoking gun is nearly perfect. Failure to open the door convinces Inspector Hubbard that Margot is innocent beyond reasonable doubt. But if the Bayes rate of guilt is high, as is the case with Tony, then a smoking gun is far from perfect. Failure to open the door leaves the inspector still convinced that Tony is guilty, as we can see here. The degree of conviction depends on the curvature of the red line, which depends on the true positive rate. With TPR equals 95%, as it is here, in other words, it is very unlikely that Tony could forget about the key in the stairway, then at a Bayes rate of 90, we have NP equals 31%. There is 1/3 probability that Tony is guilty. But if Tony's forgetfulness is more likely, let's say TPR is 80%, then NP is at 90, at a BR of 90, is 64%. There is a 2/3 probability that he remains guilty. So why does Inspector Hubbard perform the door test on Tony, knowing that he could be highly imperfect? It is because, as a conscientious law professional, he abides by what, after the 18th century English jurist William Blackstone, is known as the Blackstone principle. It is better that 10 guilty persons escape than one innocent suffer, a cornerstone of legal systems, at least in civilized countries. In our framework, we say, better to have 10 false negatives than 1 false positive. The last thing you want is to convict an innocent suspect, even at the cost of acquitting several guilty suspects. That's why the inspector performs a smoking gun test also on Tony. A smoking gun entirely avoids false positives. If Tony had failed the test, the inspector would still be quite convinced of his guilt, but at the same time he would be relieved from the moral torment of having contributed to the conviction of a possibly innocent person. Of course, the verdict is the responsibility of the court, not the inspector. And to the court, Margot is, until then, guilty beyond reasonable doubt, so much so that they sentence her to death. Margot is to the court what Tony is to the inspector, and more. But here is another interesting point. Margot's test failure should have on the court the same effect that Tony's failure, if it had happened, would have had on the inspector, lower the probability of guilt. So, had Tony failed the test, the court would probably have to acquit Margot on account that her test failure made her less likely guilty, and so no longer beyond reasonable doubt. Is this what would have happened? Well, you decide. After all, it's just a movie. And since it's just a movie, here's a final twist. This is the last scene.
As you said, Mark, it might work out on paper, but congratulations, Inspector. Oh, by the way, well, how about you, Margot?
Yes, I could do with something.
Mark? So can I. I suppose you're still on duty, Inspector.
So Tony gets caught, feels lost and gives up. But had he kept his presence of mind, the movie could have had a very different ending. "Margot, you're here," says Tony, surprised. "Mr. Wendes, how did you open the door?" asked the inspector. "With this key. It was exactly where Margot told me I would find it." What would have happened then? Again, you decide. But the point is that evidence is often not as conclusive as it might seem. Now let's look at the investor. As we said, guilt equals market return and innocence equals obscene return. Margot equals Pearl means that a 10% probability of guilt in the eyes of the inspector is equal to a 10% probability of a market return in the eyes of the investor. Carrying on the analogy, convicting a guilty person, a true positive, is like declining to buy a stock that will earn a market return. And acquitting an innocent person, a true negative, is like buying a stock that will have an obscene return. These are the two right decisions on the first diagonal. Then on the second diagonal, convicting an innocent person, a false positive, is like declining to buy a stock that will earn an obscene return. And finally, acquitting a guilty person, a false negative, is like buying a stock that will have a market return. These are the two wrong decisions. So, while for a Blackstonian inspector the worst mistake is a false positive, a wrongful conviction, the worst mistake for an investor is a false negative, buying the wrong stock. This is rule number 1 for a Blackstonian investor. Don't lose money by buying a stock that looks like a treasurable pearl, but turns out to be a treacherous pebble. Of course, not all pebbles are treacherous, and a false positive, a missed opportunity, is also a mistake. But better 10 missed opportunities than 1 bad investment, or better 10 strikes than 1 wrong swing, as Warren Buffett would put it. So let's go back to our question. What can the investor do to make sure that he's not making the possibly big mistake of buying the wrong stock? The answer is, like Inspector Hubbard, he should not try to prove innocence. He should try to prove guilt. That is, the investor is already convinced that the stock is very attractive. So, in order to feel comfortable enough to go ahead and buy it, he should not look for a proof that the stock is really attractive, beyond reasonable doubt, as it were, but they should try to prove that it's not what it looks like, that it's not attractive. It is by failing to prove that the stock is guilty that the investor can grow confident enough to finally buy it. The margin of safety derives not from how similar the stock is to a pearl, but from how different it is from a pebble. Or, as Charlie Munger, quoting the German mathematician Carl Jacobi, likes to put it, invert. Always invert. Hopefully, I managed to add a bit more substance to the quote. Thank you for watching.